Let's begin. Right, today's topic is on AE and VAE. Last time we learned about GAN, CGAN, and CycleGAN. In GAN, like the image suggested, that these images are generated from Gemini. It's quite good in concept generation nowadays. So in GAN, you have generator and discriminator, and you train your generator to mimic the distribution of data. In CGAN, beside providing the data set, you also provide the condition so that it remember to be something like a joint distribution, but still you cannot mix them. Right? And then in the CycleGAN, you kind of now more or less have the way the network that allow you to convert from one latent representation to another, right? To translate, right? Translate between unpaired image. Right? Now, for today, we will look at autoencoder and variational autoencoder. So the concept itself, right, to sum up today's lecture, autoencoder is representation learning. The idea of autoencoder is to extract latent structure, right? Extract latent vector from the data set by compressing it down through the learning process. Okay. Variation autoencoder, or VAE, learn the likelihood, learn the latent variable of the data. So instead of just learning how to map the data into latent vector, it learned the latent structure as distribution model, and then it used the distribution model to do algebra. Right? You can add, subtract, performing latent operation with that, which will be about this lecture. So in this lecture, we will look at what does it mean by latent representation. And you will see that VAE is still used nowadays in order to be able to combine a lot of semantic together in a lot of model. And then later, we look at diffusion model, the denoising process that allow you to, instead of adding, removing, you can let it learn through the denoising process. And we will look at that later on. Okay. So that is GAN, right, from the last time. If you remember last time, when we learned about GAN, GAN would use the random noise, fetch the random noise through generator to produce a certain fake image, and then you have a training set, which are real images. You try to mix them together to full discriminator. Discriminator will try to discriminate whether this is real or fake. If it's fake, then we detect as fake. If it's real, we detect as real. Then the errors from this end will be used to optimize discriminator and also propagate back to the generator. This is the way of GAN. Okay. The objective of GAN here, if you look at this type of strategy of the game theory, are to implicitly match data distribution. So you have this data set. You're trying to make generator imitate this data set, right, through by remembering how to convert random noise to the fake data. So what happened here is that generator would learn how to convert from the random noise, right, fetched through this network, and produce something that is similar to the original data. So that means the distribution itself is encoded or mapped into the generator part. And we can see that when we optimize this is the minimax, right? Minimax objective function. That is you have two objectives colliding with one another. One is to minimize the error of the discriminator. Another is to trying to maximize the error of the discriminators. Right? The two collide with one another. So you see the conflict of the objective function, which require a certain balances to have this work. And you can see that GAN does not represent anything as distribution. You don't have likelihood. You don't have PX. Right? You don't have probability distribution of the data. You don't have posterior probability, like having C, having noise, and then trying to produce PX given C. Right? Given the noise, you're trying to sampling, cannot do that because it's not the probability distribution. And make it intractable, right? And make it unable to support the more stable way of training generative model. Okay, so the consequences of all these, right, are first that the consequences is that you cannot do density estimation, right? But you can do sampling. You cannot estimate. You cannot add the noise together and then make it results in a certain semantic, right? To do that. But you can definitely sampling the noise and then generate the output. That can be done. That means you can sampling from training set, but you cannot extrapolate or even interpolate the result from the training set. Okay, so that is the problem with GAN. There is no in between. You can kindly generate something that resemble the input set, but not essentially comes from, say, it's not the understanding per se. It's more like the distribution that has already been captured from the data. So that lead to VAE and AE, right? Autoencoder, and we learn about this after GAN because it's for you to see that GAN is unstable. You can see from your work, from your lab, training GAN is tricky, right? To make it really able to generate. It can generate quite high quality data. Like if you use Mark Liu example, like the anime data, my example is translation of that. It's quite high quality data. If you compare to another, compare your author's generative models. But AE and VAE has the stability. Right? It is more stable in training objective. What does it mean by stability? It means that you get the result most of the time. But why for GAN, you have to wait and see if it's really work, right? And it has the structure latent space. Right? GAN doesn't. Even CGAN doesn't. CGAN also sampling conditionally. Right? You have condition and then you try to sampling based on the certain condition. But in this method, you have the latent space that is quite structured. That means you can add, remove, subtract, doing something that is very similar to embedding, in inward embedding concept, that when you have latent representation, you can find a kind of doing algebra to get the meaning out of that. Okay. And it has the probability interpretation for the data set, and inference itself would be mapping data to latent. Okay, so converting data to the latent, not competing in the game theoretic way. Okay, so these are the reason, right? And then there are also some application that GAN fails, and then we move on from GAN. Like GAN doesn't do well with data compression, with anomaly detection, with representation learning, with latent space, with something that relates to uncertainty. Okay, so these are, well, GAN are good, but it cannot do something like this. It cannot have latent of the man with glass minus woman with glass, supposed to be woman with glass. And then add woman without glass, you have man without glass. This is from the training result, right? But I suppose I have to train more data. But yeah, so you can do this. You can do this in the, you can perform this in the latent space and then have the result produced according to that. And now you can imagine if you were to add this together with the language model, it can then transfer the semantic from the language model, right? The language model into the combination, into the sentence, and then you have like combined latent vectors to produce the output. Okay. Right, so now we have competing philosophy of generative model. We start with GAN, the first one. So in GAN, it works like training as adversarial. Whether the game the agent can distinguish real or fake or not, then try to improve through competition between the tools. And you can see a multiple strategy of using GAN, like in CGAN, in CycleGAN, in AutoGAN as well. But most of them would learn, it would not have the explicit probability model. What does that mean? It doesn't have the distribution, representation in distribution that you can do something like I showed you earlier. Okay. All right. That means that's why we move on to have some types of internal representation. In the likelihood-based model here, the encoder, you have encoder and decoder, not discriminator and generator. So the role changes from competing with one another. You have two roles. Encoder network would encode image data set into latent representation. We look at AE first, the autoencoder. And then for the decoder, right, decoder will, decoder will transform the latent representation back into images. Supposedly, the same images that you have earlier for the autoencoder. And after training this with a lot of time, you would have the latent variable that can be add, minus, subtract, like that. Right? So this is the idea of variable in the autoencoder, right? The likelihood-based model. So instead of having two networks competing one another, you have two networks. One encode or compress the data down to latent representation C, and decoder that expand from latent representation C back to the image. Okay, so that's VAE, the end goal that we are going to, but we will start first with autoencoder VAE. Okay, so from all of these, you see that VAE output will allow you to be able to, it will be more coherent, because when you generate the data, it actually takes from certain distribution, not generate through the network. That means the sampling process to produce more coherent output. It preserves the structure where you have the distribution, and the output looks smoother but blurrier, right, than GAN. Right? The blur image occurs because it has, we have like Gaussian likelihood using a pixel. Each pixel is treated independently, and we actually perform mean prediction from the distribution. Okay, these are the reasons that the result would look like this. If you compare GAN to VAE, VAE will look quite smooth, blur, right? GAN will look quite sharp. You use GAN generate the high quality image. The reason is here, right? Because it has, but it can perform latent geometry. I mean, I said latent algebra. It is able to perform linear interpolation. Also valid in when you sample some noise, it is able to generate kind of in between the space. Like you have the space between varying class, not varying class, you can get into the middle somewhat, right? And this is, we are able to do that by modifying autoencoder with the three things. By having likelihood estimation, having KL regularization term in objective function, and lastly, performing reparameterization trick, right, in the data representation, which we will see each of these later on in VAE. Okay, let's start with the basic one first. Right? What autoencoder? Right? An autoencoder is a type of network that initially it was thought of used to have in order to clean noise. Right? In order to just clean noise, to perform the noising, compress the data down, having better representation. But later it was found that okay, modification of these is very useful when you want to perform generative deep learning. You have data X, right? You have the data X, and then in order for autoencoder concept is that you can compress down this data X into a low dimension latent space C. Right? This low dimension latent space, think about like, this is like 256 to 256. Latent space can be 1 times 100 element vector, for example, or 300 element vectors. It's a lot lower dimension than 256 times 256, right? And then you then train the network in such a way that it would produce the same image. Now it's easy task, right? You already have data. Then to train this network, you just put the same data as input and output and try to train it to encode down. The encoder can be fully connected, either fully connected, actually it can be fully connected or convolutional, right? Both are fine. It can also be, if it's not image, it can also be a recurrent network of sort as well, which is used in the early day of encoder and decoder scheme in machine translation before the era of transformer. Okay, so you have encoder. Encoder will reduce data rate down to this. And then the decoder will use this latent space and produce the same image. Then objective function to train this network would be mean square error. So the two images should match. So that means the loss of autoencoder would be x minus x bar square. And then everything is easy now. Just training parameters in both, on both sides. I think I have an example on the lab, which I think after autoencoder, I will show you first, and then switch back to look at variational autoencoder, and then go back to the lab again, right, for that. Okay, so we will just move past through this very quickly for autoencoder, how it works, and then just go to the VAE, because we are not going to really look at it as much. We have the from the VAE here. So what we learned is that we can compress it down. Let's look at the lab, then we can look at the content, like for fun. You can read through, okay. So for the autoencoder, we will perform autoencoder with the to generate digit. Let me zoom in and then show you that. Increase the font size. Okay, I should click here. All right. Okay, so we start with the network, right? That would compress the data down. Note here, if the first example, you can just take Mark Liu notebook and run it. But for the second one, you need to download the data set first and then prepare the data in a way based on his previous lectures in order to use it, right? So do that back home because there are quite a lot of steps. I can actually just put everything as automate, collab, like doing the script earlier part, but it takes a lot of time to train, and doing it on collab wouldn't work now, to show you here. It can work, but you have to wait like an hour for the 10-15 epoch. Right? So it's quite a long time. All right, here, so we start with using MNIST dataset. I already have it here, MNIST dataset, so it should be fast. This is MNIST dataset, which will be transformed, just convert to tensor directly. Okay, the trend set and the test set of the MNIST dataset. Then this script would set the batch size to 32 samples, then configure the data loader, which will be used in the training. The data loader load data in batch and use in training. Okay, you just put in the set that you want to use, the batch size, make sure you want the data set to be shuffled before use, very neat. Okay, then the next step here is to train the model. I used CUDA here. And autoencoder network, let's take a look here. Input dimension is 784. Right? Z dimension is compressed down to only 20. And H dimension is 200. And let's look at how we use it here. So starting from input dimension, this AE receive input dimension, C dimension, and H dimension. And then we use first the linear layer to receive input dimension and convert to the hidden dimension. And then afterward, encode layer, this is common layer, and then the encode layer receive the output of H dimension and convert to C dimension. So it's just one very shallow autoencoder. Can be deeper if you have a complicated data set. And then L1 here, linear from C to H dimension. And then for the decode, it converts from H dimension to input dimension. So this is all that this autoencoder initialize. You can see that it consists of compress it down and expand it up, right? So these are the thing. And then we have encoder function, X, which you can see that here are all the linear, and then these are stored in common, encoded, L1, and decoded. Encoder function receive X and then pass it through ReLU, and then call mu of self.encoded common. Okay, so it passing ReLU and then calling the function again, encoded, right? This is encoder, encoded. Encoded is here, which is the linear layer. So passing ReLU and then fetch to linear layer, you get mu, return mu as the result of the encoder. Remember, encoder compressed down, right? So it used encoded here, right, to compress it down here. And for decoder, use the C, the noise or latent space, and then pass it through L1, which is the linear that receives C dimension, and then expand to H dimension from 20 to 200. And then you have out as 200 and pass it through sigmoid, the output layer, and self-decode as the decoder. This will be the output of the decoder. Now, these are very simple script to compress the network that would reduce the rate and enhance the rate. Right? When you run it, then this will be the function that would put input to output. Right? Receive input, and then what it does would be calculating mu from using encoder X, calculating out using decoder mu, and return both out and mu. Right. So these are autoencoder. Then we use autoencoder. Okay, did we run it? Yes. In the autoencoder function here, we move the model to the device, setting learning rate to 0.00025, and then use ADAM to optimize all the parameters of the model here using this learning rate. Okay, then it's time to train the model. In this, we try to collect the sample. In the test set here, this collect a sample of each digit in order to iterate through. You can say that when we come to here, we have the IDX set to 0, and then passing through the loop for each of the train set, and then trying to get it to append as the data set that we used in the original here. And then the result would be this figure. The result would be this figure that show you in here. Then we plot the reconstructed, right, comparing to the sampling of the model. Okay, then plot digit. Okay, plot digit will show you the conversion from digit and the latent space here. This came from out and mu, right, of the model IMG to device. By putting it to the device, now we're trying to see whether it can reconstruct or not. Right now, not yet. It has to be trained at first. This is the training loop for each epoch. We have IMG move to the device, and then forward pass, right? Out mu pass through the model, and then compute the loss, sum of square error, and then optimize it, set 0 grad, loss backward, and then optimize the stat, right? The same as previous lectures. And lastly, tabulate the loss item, and then repeat again for all of that. Okay, so this is first epoch. You can see that the results look blurry, but you already get it in the training. And then if you look at this is like 1.8 million, the loss function, then it reduced to 870,000, 700,000, 600,000, down to 10 epoch 9, 400,000. And it can now replicate the result quite well, right? That means it's not producing random noise anymore. Right? When you put 1, it can compress to the C, to latent vector, and then from the latent vector, it can then convert back to the output that you see here. Right? So compression work for autoencoder. Okay, this is to save it, and then here is to load it, and then plot the result. Okay. Now let's look at the failure mode of this. Let's look at the result here first. Okay, so latent coding Z that are learned in autoencoders has certain property. It encodes information, encode useful information for the reconstruction. You can see that it can produce quite accurate original image, generated image that is close to the original. However, it doesn't currently interpretable. You see later on here, and the representation often entangled. It cannot tear apart the semantic layer, the meaning in the representation once you get it. You see later in variational autoencoder that once you have multiple modes represented as latent representation, you can then play with the meaning play with the meaning of the representation. That is because the reason that that is the case because AE autoencoder does not know distance. It doesn't know whether one distribution is different from another distribution. It doesn't know that. It just remember the AE. It just remember the vector. Think of it as one vector is quite independent of another one. It doesn't summarize things as patterns. Patterns mean distribution that you can say that these are repeated. So you have certain distribution with them. And it doesn't support smooth transition. The reason is because it doesn't know the distance. It cannot represent interpolation. So that means also once you random something, it cannot generate output here. This is real and reconstruct. But if you were to sampling Z and use the output to generate, you get this mumbo jumbo whatever here. And that's even though you're trying to sampling something close to the real reconstruct here, it doesn't work. Right? So latent doesn't mean it has semantic. It has representation underlying that, but it doesn't have semantic yet, but it can be. You can make it have more meaning in terms of latent space. That it know the distance, it know that one differ from another, and it can learn the context. Right? The key would be that it can learn the context, the meaning inside there. Okay, so that is why when we talk about AE autoencoder, it is often not referred to as generative model. I used to teach this in the deep learning ever since like 2018, like that. It was thought about it as like a technique, like the way that you configure the architecture so that it compresses data down, quite cool, and then you can regenerate it back. And now there are a number of methods like UNet, like a number of other techniques that come afterward that perform compression, expansion, similar to AE. Right? But it is not generative because it doesn't have prior, it doesn't have likelihood, it doesn't have marginal distribution. That means sampling Z is unknown, it's out of the bag, it doesn't know how to generate the output. Right? So not generation principle in there. Okay, so what does that mean? It means this is like the core of this course, somewhat. Right? To have a generative model, it must have semantic. You need to have prior of the latent variable. And then you can then convert the prior of the latent variable into Vx given C. Right? From C, you can convert to X. Right? This is probability of, think about a chance and you get certain results based on noise profile. So this is like converting from distribution PC into Px given C. And then you need to be able to also find the Px distribution of the image through the integration of the using conditional probability relationship. Finding, this is from Bayes' rule. You can find marginal distribution by finding how often that X happened because of C like that, which is impossible because you wouldn't know how many noise profiles are there. How would you be able to integrate all of them? Right? There are a way that allows you to approximate it, but theoretically, generative model, you need to be able to find probability of the output. You train the model with X, you train the model with certain images. You should have distribution of image, not just a pieces of them. Like you have multiple faces, you need to have daily distribution of it that you can sampling and have the face distribution. So autoencoder doesn't have this. Right? That is the reason that this failed. If you look at the code here, First row would be real MNIST, second autoencoder reconstruction, and third comes from random noise. Okay, this is random latent sampling. CRAN comes from torch ran n, random it out, convert to device, and then pass it through decoder. You get XRAN, then plot them together. And then this is the result. Right? You get jumbo image output. And the reason is because it doesn't represent the transition or cannot convert random noise that is not in the set of images that trained in the model, and then be able to infer from that. Doesn't work that way. Okay, that leads to having this, right, VAE. So that means if we have all of this and we want to generate an image, the step to generation would be, first, we would sampling the latent variable, sampling noise profile from the distribution. And then actually there is the step 1.5, doing algebra, doing geometry, right? Subtract, add, whatever there to have certain meanings that you want. If you have experience generating image, there are, like when you add, there are times you add tag in with the VAE in order to, or with LoRa in order to remove those latent variable out. Right? So it's kind of like that, right? Doing that before generating observation, that is sampling again the distribution of Px given C to get X. Then it means you perform two samplings. The Z would capture the underlying factors, variation inside, and X would be noisy observation from this. So it can be represented in right-hand side here. You have Gaussian distribution, then sampling it to have a certain representation, and then pass through decoder to get generated output. I thought this is how it worked. Comparing AE to VAE, the difference is not subtle. Right? They are quite different here inside. So beside here is very simple, right? In your code, you can see that it works very simple way. Right? Here you have input and output, but the encoder, instead of encoded into just latent vector, it now encodes into mean and standard deviation. And then once you encode it into mean and the standard deviation, you treat it as distribution. And to generate something, you sampling from the distribution of the latent space and then put it to decoder. This sampling use the C equal mu plus sigma times epsilon. Then you sampling epsilon, certain epsilon, certain noise there. Right? Sampling noise here. Right? When you train the model, you use the same image though. Use the same image, and then you're trying to learn mu and sigma through this combination. Why this C equal mu plus sigma epsilon? We will look at that later on. Okay, so there's reconstruction here. And then when you want to generate new output, you just sampling N01 and then put it through the equation here. Then you put it to decoder. Then you get result. And so the process is very like random generator that you use in your computer right now. If you want to have beta distribution or Poisson distribution or log normal distribution, what you would perform would be sampling from, that is N01 though. What you do in computer is like sampling from uniform sampling first and then convert it to such distribution. But well, there are sampling random, pseudo-random algorithm that concern that. Okay, so this is the way that allow you to do that. And then in the optimization, there are two constraints, right, per se, two objectives. The first one is that, but you have just one loss function, one optimization objective in one equation. In Minimax, you have two colliding networks that trying to perform different things. But in variational autoencoder, you have just one network, right? One encoder-decoder network, optimizing through one objective function, one loss function. But this loss function would consist of the reconstruction loss, comparing input with output. And another would be the KL divergence loss. This is really important thing. Right? Otherwise, you would just have autoencoder. Right? The KL divergence loss measure distribution distance, measure how grouping is done in terms of the latent space, and it allows the similar concept to be grouped together. You can see that just adding the concept of distribution and have a more sophisticated way in sampling here. It allows VAE to generate the result that has variation, but have the same concept, more consistent output. Okay, so this is the way that it is done. Right. Can model an unobserved cause, right, and unobserved event, while that AE used for compression. Right. We will look at the concept of VAE throughout this to the end, and then we will switch to the code later on. Right. So doing VAE, inferencing means computing latent space from image. Right. If you remember back in classification, when we call inference, would be reducing data rate to some representation. Here as well, inference here means you want to convert from, say, a bunch of images. You want to convert them to mean and standard variation vectors. How would you do that? How would you do that? Right? It's quite complicated. It's quite complicated issues to do so. So here, given latence variable model, what we want would be PC given X. Okay, so PC given X is given X, you get latent space. So this is an encoder part, right? Inferencing part. But doing the inferencing part theoretically correct exactly is hard. The reason that it is hard because if we look at Bayes rule, in Bayes rule, Px given C is PC given X, PC over Px. This is probability of having this image given a certain noise profile. How many noise profiles are out there? Do you know that? You have like infinite number of noise profile. And then you have to have marginal distribution, Px, like distribution of images, if you interpret it in human language. These are like distribution of your data. You have to integrate of Px given C, PC. How many PC are there again? That means this cannot be done. Right? It is intractable. You cannot really do that theoretically. Right? Because you have dimensional, high dimensional latent space, how would you be able to sampling everything? Right? And you also have nonlinear decoder, don't forget. Even though you find somehow to be able to integrate it, you have nonlinear encoder Px given C. That's neural network. Right? And then that means there's no closed form. It cannot be done. So what do we do? Right? Usually computer engineering, when we encounter such a problem, we will just throw the problem as approximation. Integrate too hard, approximate it using numerical method. Can be approximate. Okay. Approximate how? Okay. So there's like approximation as probability distribution. So when you see this, you can see that the topics of VAE require quite a deep understanding in statistics. Most of the techniques here are statistics. Even like from the basic one, like the C score, the calculation of the projection from N01 to a certain not zero mean distribution, right? Using C equal mu plus sigma multiplied by certain random variable, like projection, to this approximation. Okay, so the inference is learned. So instead of, basically we are saying that we are trying to learn the inference. We are not going to compute it using some formula. We just train it out through the same method, right? Train it out through the same method. That means we choose this encoder Q of C given X and say that it has normal distribution, Gaussian distribution, mu phi x and sigma square phi x. Depending on x, mu and phi will be different. Oh, sorry, mu and sigma square will be different. So it would then encode x into mean vector and standard deviation vector, depending on output, depending on input. It receive this function receive input, convert to mean vector. This is basically the network that we are talking about. It has two objectives. One producing mean output, another producing standard deviation output. Yes, that's it. So it has this mean vector. So it instead encoding into just one mean vector, it now encodes into another standard deviation vector as well. And then instead of just use them directly, it has here the sampling process. But sampling process only work with reparameterization trick that we will talk about it next. That is, you use C equal mu plus sigma and then time epsilon, then sampling from that, and then train with the reconstruction lot and KL divergence. Okay, so the network look like that. You have VAE encoder, convert to mean vector, and then these are learned and standard deviation vector. And then they are combined and then sampling. You have latent space. And you can then sample 0 and 1 and then convert to VAE. Sorry. You can then train it. When you train it, you can train it through the loop here. The blue and then orange here, latent vector C and then VAE decoder. When you want to generate output, then you can use combining mean and standard deviation again, and then sampling from the latent space, sampling from N01 here, N01, to get different result. That means everything here are learned, and then use encode inside the network. So compare this to AE. The difference would be VAE combine sampling process, the entire sampling process and probability distribution into the inside of encoder and decoder. Right, so this is what is done. There is no such thing like that in autoencoder. Right? There is no you can generate random number out here, but it doesn't work, right? But what VAE does is to put the sampling process and statistical distribution, just probability distribution, normal probability distribution, into the inside here. Now it modified the network to have such a very elegant, right, such a way that it can combine the parameters. It's combine the latence variable together. Okay, so it learned probabilistic mapping through continuous structure, latent space. These are structure, latent space, allow it to compress compression and generation realistic data. Okay. And now, okay, so these are the structure, right? And these are the network, encoder network, you have decoder network. This should work the same. Now we have the sampling, so it shouldn't differ much. Now, but the different part will be the loss function. Instead of having just MSE in AE, now the loss function will contain two parts. One is still some square error, the mean square error, MSE. And that represents reconstruction loss, the data loss that can be measured. Another is to measure distribution similarity. Why do we do that then? Because we want to have the distance measurement based on KL divergence, so that if they belong to the same distribution, they should have low distance. If they belong to the different distribution, they should have high distance plus large loss, right? That will be quite loss values. Okay, but if they are close to one another, the same cat with the same breed, the distribution would be similar, image would be similar, or somewhat. Image might not be that similar, but distribution would be similar with the same pattern. Okay, so that's the idea. Right? You have two terms, one for data reconstruction loss. Another is to have the distribution measurement, distance measurement. Okay. And Gaussian is used, but because we use Gaussian, you see that it creates a situation that it creates blurred image, because Gaussian means you sampling mainly from means, and that also happens. The KL divergence, right? Callback Lieber divergence asks this question on how much information we lose if we use Q instead of P. If we use one distribution instead of another, what would happen? This is the image that's showing KL divergence. You have PX, like this is target probability that you want to compare, aka the network distribution latent representation you already have trained in the model. And then you have the learned probability. You want to identify whether they are divergence would mean that they are different from one another. So this would be encoded into this is the formula for KL divergence. Just look at that. It's like proportion between distribution, right? And then time log odd log distribution, log proportion, and then multiply by the PX itself as the percentage or the part that are related to X. Okay, but we look at that, how that adapt into the loss function. Okay, so now let's move on. Right? So that means we cannot. So we now have two terms. One is error. Another is distribution difference. We know that now, right? But still, we still cannot learn from this directly. We still cannot learn from the distribution. If we forget about this first, you cannot learn about distribution directly. So we want to learn generative model Px given C. This is the part that I think I make a switch a bit. Generative model is PC given X. Inference model is Px given C. Am I right? Oh, no, I'm wrong. Sorry. This is already correct. Yeah. Again, in generative model, you generate X from noise. So that one is already correct. And in inference model, you generate noise or latent representation from X. Okay. We want to learn both of them. The constraint is to ensure that latence variable follow the certain prior distribution, and direct maximum likelihood maximization optimized directly cannot be done, too complicated. So we need to approximate it. The way it is done through is called optimized lower bound. The technique itself is called elbow, right? Elbow objective. Okay. Let's look at the objective first. What we try to do it in the network. If we were to do it in an ideal way, right, we want to find max of log p theta x, and then we want to maximize this is the information, right, the information of the distribution x. We want theta to represent x, so we have to maximize it. But we cannot do it due to this intractable computation. These are the reasons I already mentioned. The key idea here, right, is to find, so instead of maximize log px, we want to maximize the lower bound of log px. Okay, this is called elbow, evidence lower bound. So it works in a way, if you think about the concept, it's like big O notation. In the big O notation, you have a lower bound of, right, a lower bound of complexity. This is not that, but it's the lower bound of the function. Elbow will have to be less than or equal to log p. So if we can maximize elbow, then it's all great. So the way that it works is that we now define elbow function as two parts. It consists of the data fidelity and latent regularization. Okay. Data fidelity is expectation of log p x given c. What is this? Generator. Generate and you have the same image. Right? This is from generator. Given q c given x. Okay. Now this is the part that relates to data fidelity, and minus KL. So these are errors. These are errors. Minus KL of QC given X and PC. The divergence of QC given certain X and just property of C, of noise alone. So we use it to represent the difference. Then each of these has certain meanings. Reconstruction term, I already explained it. Log p x given c. This would be an expected log likelihood. How good the model represent the data. It measures how well the decoder explain input. And this is the reconstruction loss. This term, when you convert it to the real calculation in the Gaussian terms, it would be the mean square error or the square error loss, just like in regression model. Okay. If it's Gaussian. But if we talk about generating random data from not Gaussian, Gaussian means you generate 0 and 1 and profile and then use it out as output. But if you were to generate a Bernoulli profile, a Bernoulli profile would be not Gaussian, not continuous, but it would be more of the property of having 1, 0. Right? Then you have binary cross entropy in loss. But in any case, we use Gaussian here. Okay, but Gaussian would cause blur, right? And if we use it only, right, it would be blur. AE also produce blur. But if we use this term only, you get AE. The same thing. Right? Because essentially you are doing optimization based on only data, and the encoder wouldn't be able to capture distribution similarity. But we use both, right? So this is just to show you the square error. You have input and output. What we want to train is latent space. Reconstruction error meaning that we are compare point by point and then calculate the square error and then sum them to have the mean square error. And so this is very basic step of mean square error. In the KL divergence term, this represents the posterior probability. This trying to have the posterior probability close to the prior. That means posterior is the X, and then prior would be the latent representation. You want them to be similar. That means if you have an interpolated version of prior, you should have interpolated version of posterior of the output. Okay, and create the smooth interpolation, share and trend structure altogether. So the KL divergence, by assume that they have normal distribution in the KL divergence, I'll just jump the math here to the representation in terms of number. You have mu I square for each I. You have mu I square, sigma I square, and log sigma I square, and then minus 1. This would be the KL divergence term. And then combine them together. So think about them. Think about this. MSE represents loss. The more it has, the more error that the matching occur. Bad model. Then adding with this. Minus, right? Minus KL divergence loss. The latent regularization have mu square, the summation of mu square and sigma square. The more value that you have in the latent space, right, the more regularization, just like in the other. So you have more value, you have more errors. But this is like to subtract it out of the original one. Subtract it out of the mean square error. Okay, last things, right? Now we have like two representation in error in the objective function. One is data loss, another is the distribution measurement, whether they are belonging to the same distribution or not. Lastly, well, the technique is referred to as reparameterization trick. Right? This is very straightforward, as the name suggested. You would reparameterization. You would trying to create a new parameter. This is the trick, to create a new parameters. So instead of sampling directly from the Gaussian, from the normal distribution n mu sigma square, which you have sigma square as vector, that wouldn't work. Right? So many of them, of the mu value, of the sigma value. Reparameterization trick, treat it as sampling of n01, and then you then convert to C. The trick allow you to now using derivative. You can differentiate that function with respect to mu and with respect to sigma. And this allows you to bridge the gap between decoder and encoder. Remember, if you want to take the derivative of something, right, it should have equation connect the two together. Otherwise, how would you calculate the dip from the error and then propagate the error back to the input network? Right? So here, this is like random error, randomness, introduced by epsilon here, and mu and sigma deterministic here. So this is the reparameterization trick. Right? So we in the forward pass, you calculate, well, put data through encoder, pass through mean and standard deviation, calculate Z. From Z, then you can put it through encoder, decoder, and then get the output. Then once you get the output, compare with the input, you will get gradient, and the gradient will be backpropagate to the decoder network, backpropagate through deterministic operation here, and then update mean and standard deviation, backpropagate to encoder. So it's quite cool, because now you kind of, because otherwise you would have n of parameters in the middle that you have to sampling a bunch of them which are not differentiable. But with this, it's kind of combine everything together, and then what you would optimize would be the mean and standard deviation here, and through the link from the reparameterization. And with this, the mu x will be learned through as a latent mean. Sigma x will be latent standard deviation. If sigma is large, you have more uncertainty about the factor. If sigma is small, you have quite confidence in the encoding. These will be encoded through the two parts here. The part that are about encoder and the representation in mean and standard deviation. Okay. Oh, plus, sorry. Yeah, I wonder why it is minus. It should be plus, adding together. Because like more error, bad. Larger parameter, regularization usually mean bad. So combining them, bad, yeah, it should go into the same direction. That means please fix the equation I have earlier as well. Should be plus sign. Can you have like loss from reconstruction, loss from latent regularization, and you have beta here to control. If beta is 1, you have standard VAE, combining both together. If it's not 1, then it's called beta VAE, that you kind of have some control over the divergence of the error here. Okay, right. So those are the way that you can optimize and create the representation, learn the representation. Now we will look at why it fails. Then we move on and look at the code. Okay. Or should we look at the code first, and then we look at the failure mode later on? Right. Let's look at the code first instead. On how it works, and then we can look at the failure case. All right. Okay, the first part I already did, and I already did this line of code. These two lines are, for me, taken from the author notebook. Okay, I start with this. I create a transformation. Resize is 256. You will have the face glass and face no glass, right? Face no glasses and face with glasses. These are the dataset image folder here. Create a data set, create a batch size of 16, load to the data loader, and then set the latent dimension 100. It is just 100, and here is the encoder. The encoder would start from the part here. Encoder would convert from 256 3-channel to 128 8-channel. Okay. So from think about it as the think about it in 3 dimensions. Right? You have 256 by 256 by 3. 3 are the color channels. Then convert them into 128 by 128 times 8. Okay, times 8 channel. The next convolution. Okay. From 3-channel, convert to 8-channel, and then also reduce it by 2 by setting the stride convolution. Stride means skip one step at a time. Right? So you get reduced the rate to 128, and then again here doing batch normalization, and then attach with convolution number 3 here, 16, 32, and 3, and then try to again reduce rate from 64 to 31. Padding 0, get 31. Then linear layer, stretch them out from linear layer, then map them to 1024, then to 100. Okay, you have linear layer 1, 31, 31, 32, and 1024. Layer 2, 1024 to latent dims, and layer 3 as well. And then you have, lastly, you have n from distribution normal and move them to CUDA. And then this is like the initialization. And then in the forward pass, you get the input X, pass it to GPU, move it to each layer, convert 1, batch up convert 2, convert 3, flatten, and then you get here of linear 1, LELU, you get X. Then the reason that we have linear 1, linear 2, and linear 3 is to encode it to mu and standard deviation, linear 2 for mu, linear 3 for standard deviation, and then compute C as mu plus standard deviation times self and samples mu shape, a sample from distribution with the shape of mu. So this would generate random noise and normal distribution, the shape of mu, 0 and 1. 0 mean standard deviation of 1, the Gaussian. And then return the mu standard deviation vector and see as the output. So this is the forward pass for encoder, right? And then for the decoder, decoder would work in the opposite end. Right? It take the latent dimension and then revert everything. You get linear LELU and then linear and then LELU. These are for latent dimension up here. And then unflatten it and then perform convolution, which the convolution consists of sequential of convol 2D, 32, 16, 3, sliding 3, output padding 1. And then do it in reverse process. So at the end here, you will get a pass it through sigma as well. At the end here, you will get 256 times 256 times 3. And so you can see the reverse in order, very similar to autoencoder. All right, that means the difference would be that now you have mu and standard deviation and convert to reparameterization trick. All right, and the VAE consists of encoder to the latent and the decoder of the latent. These are the VAE. Right? Put input. These are the VAE. And the forward X would be X move through this, then you compute mu standard deviation C from the encoder, and then decode them, right? Decode them from mu standard deviation, then decode C from the conversion. So these are the VAE. So you can see building the model, right, in this. This is very similar to what we did earlier. We try to write the code as the single case. And you can see here that we kind of create a code that would work when you run in a single case. And then you will define parameters, say it's optimized, put it into the epoch to train. Okay. And now we initialize VAE here, which consists of encoder and decoder, learning rate LR, and then put into the optimization ADAM, and say these parameters will be optimized with ADAM method. Oh, I forgot to initialize. Ever since here. Okay. Then it is the training, right? The training for each epoch here, initialized VAE train. Okay, the VAE that we create here from NN model. Epoch loss start with 0. And then for each image, from each images, the batch from the loaders, we then move it into the device and then plug everything into the batch, into VAE, and get mu standard deviation and output. And then compute reconstruction loss, like images minus out square, the sum of square error. And the KL loss, standard deviation square, mu square divided by 2, and then minus log standard deviation and 0.5, and sum them together. Very exact of what I showed you earlier, right, in terms of the equation. Then combine them by the loss. I should have beta here, but you can try that later on. No beta for now. Optimizer, 0 grad, loss backward, optimizer step. And so set the gradient to 0, loss, right? Compute back, you have already compute forward, then compute backward gradient, then optimize, update the parameters, then add item to epoch loss. So this is what will be done when we call it. And each plot will just, you can take a look, it's just plot the output, right? Show you the output, right? From random some number, and then put it to decoder to show you that whether face look like face yet. I will look at that. Here is the real epoch. Okay, let's wait and see a bit. One epoch take about, for in this computer, I think one epoch takes about 1 minute or so. Doesn't use much of the RAM though, because the data set is quite small. Processes are really limited here, and I haven't increased the model size. So in terms of the memory, it only takes like 1 or 2 gigabyte. So you ask me, running in Colab should work as well, but setting it up is quite tedious. Setting the folder structure in this example, because well, in Mark Liu notebook, you are supposed to follow his notebook one by one, and then you will already have the structure set up. You cannot just jump in the middle. So I just use this version of his. That means I have to go back and see which line, I already put it here, which line that are setting up the folder structure when you download it from Kaggle. And then after that, it works. You can duplicate the results here. Okay, right, first epoch. How many? 38 million. Right, this is loss. Look like face, right? And glass? No. Look like face. Let's wait until the end. For those of you who are online right now, if you have questions, type in the chat. Actually, I pop up my mobile phone. I should see what you type if you have any questions. Okay. So AE, learn representation. VAE, learn representation, but better. Learn representation in a more cohesive manner. Cohesion means that more consistent manner, and that allow you to group those that are similar to the one that are similar. Okay, and when you look at this, you see that I did not separate the data set into class. No, I did. Then I know that class, no class here, a bit, right? So these are the faces classes. Right? Here is separate into classes and no classes, and no classes on both of them, G and no G. And now the second epoch result is out. Now you can see that the distinction between hair and face becomes clearer in a lot of them, but well, they will be blurry. If you try playing with VA alone with, say, the current latest generative AI, you see that they are still blurry. They can respond to the prompt, but they would produce blurry output. I think I will try that and show you in Comfy UI later on, once we try to combine things together to use more quality-wise version. Okay, so while we are waiting here, now we see glasses. See face with glasses, face without glasses, face that looks women and face that looks men. Okay, while we are waiting, we will cover that. So how would, now you see how they combined, right? How would the model collapse? Right? There would be some point that the model wouldn't work. Okay, it is more stable, but posterior collapse, meaning that a posterior refers to unable to generate here. When you have PC given x, approximate PC, what that means? What does it mean? It means that your conditional probability, the inference part, is just noise. Doesn't learn anything. The encoder network just gives you noise. So it's not good, not grouping into distribution. The KL part becomes 0. So if the KL part becomes 0, it indicates that your model would be AE. It would just be deterministic AE. Right? And decoders ignore C. Right? You produce C, doesn't really able to produce coherent output. Okay, so these are the failure case. So in a way, all of these means both encoder and decoder do not learn anything. It cannot distinguish distribution from one another, and it revert back to become autoencoder. So that's how it failed. Okay, so that you can see that variational autoencoder put a lot emphasis on the ability to regularize the objective function, to have separate distribution of each meaning, right? So that the latent variable would group together. Okay, so the symptom that you will see would be latent variable carry no information at all. Convert here, carry no information at all. This first one, it means carry no information, because xc given x become vc, just distribution of noise. Model behave like unconditional decoder. You cannot add, delete, not delete. You cannot add, subtract, and then generate decoder with some consistency. So that would be the symptoms. Okay, this is posterior collapse. Instead of having two distribution and being able to combine them, you have just one. The encode, then you have just one. Generate, you just have that one. Doesn't matter, right? But become reconstruct a good cat in the middle. Yeah, don't see different though. And maybe I should use some different image as the combined version. Maybe different color. Okay. All right. How far along are we? Okay. Looks great. This is epoch 5. Why is VAE more stable than GAN? Right? One of the very important questions. We learned GAN before. GAN compete. How does VAE becomes better? The first thing, game theory is nice, but it creates dynamical system instability. Right? When it have like the two player try to compete, it looks great. Right? You use just one, right? And you use just the generator. But in VAE, you have a single objective function, just one objective function. Oh, this is supposed to be plus. Okay. But probably divergence, not similarity. The other one would be that one. Okay, so say just have only one objective function, and then you try to optimize everything together. Jointly optimized, no adversarial game, more stable. That's the first reason. The second reason is that, again, the same thing, no minimax competition. There's no competition. The encoder and decoder work in cooperation. There are cooperation between the two, right? So it is more stable between the two. While in GANs, one try to compete with another, it fails. Right? When you collaborate, then it works. Thirdly, it is more stable because there is no discriminator collapse. In GAN, there are more than one point of failures. So you can say multiple single point of failures. If discriminator fails, generator also fail. So you don't have discriminator to worry about to learn. The decoder to learn. And because you have the decoder, you don't have discriminator, you have the decoder. Right? Okay. And you have this reparameterization trick which allow continuous gradient. It allows you to combine mean into C and then mix together to produce decoder. So with this, it kind of allow you to enable gradient descent to learn through the stochastic node here. These are stochastic. Well, usually when you have sampling nonlinearity like that, it is very difficult to just learn the parameter because there are chances. You don't know what are chances there. But with the combination here, you can just ignore randomness and then learn the parameters here. Right? So by learning the parameters through the combination here, you backpropagate to the mean and standard deviation and the encoder network. So these are the reasons why VAE are more stable. And here, give you quite decent output as well. Now epoch 7. This is 11. Yeah, 10 epoch. So wait until the epoch 10. Okay, and if you compare to autoencoder, right, it is now becomes generative. Autoencoder is not generative because autoencoder, you condition input X, certain X, has to produce X that looks the same. Okay, use reconstruct. This is reconstruction. Can the model explain this image using certain C in the between here? While for the generation, in the generation, you don't have condition. You don't need to put in X. You just sample. Once you perform sampling, you can then generate. You can create possible image through just sampling. You can see that earlier in autoencoder, I cannot sampling and produce digits, right, that are coherent. But now you can. I didn't use digit to show you here. Take quite some time to train. Now epoch 8. Because now Z is sampling from N01 and then put through decoder and then you get X. That means you can just sampling C, put it to decoder. Actually, sampling C, do the reparameterization and then put it to decoder and then get X. So C come from reparameterization and get X. Then this is, you are able to do this once you do that. You can do linear interpolation. You can have C1 plus C2 and then with a certain weight. A little bit of wearing glasses and a little bit of having certain aspects and then combine it to C and then put it to decoder to get the combined output. Right? So now it now has semantic because it has meaning encoded through this. Okay, so it has latency continuity, certain semantic smoothness, and it works because of posterior distribution. Now becomes overlap. There is no disconnect here. Okay, there's no disconnection here. And KL would discourage isolation of latent regions, isolated latent region, discourage just having no meaning, because if you encode and then it close to a certain distribution, it would be mapped into just the mean vector for that distribution. And latent space would approximate Euclidean space. You can add, not delete, add, subtract doing here, doing interpolation like having CA, CB, interpolate between them and put them in the CA, you get this image, CB, you get this image. You can have a range in between. These are interpolation which are close to one another. You see quite a number of these in the paper. If you look at that, there will be like interpolation of one scale to another scale to see that it conveys certain meanings. Okay, done. Now these are the output. Okay, a little bit blurry, but now you can see rich, you can see face, you can see different hairstyle, you can see feature quite distinctively. Now we are going to combine them, right? Combine some face, subtract some face, and see the result. So this is to load it from another one. This is downloaded from elsewhere. I'm not going to use it yet. We will use, this is compared to the original with the reconstructed. The original reconstructed. Right? So it can reconstruct to a certain degree. Right? Not so close, but quite close. So it still contains glass, still looks boys, still have glass. Okay, so that means latent representation can now represent like from this, putting this image into encoder and then do the forward pass, right? Do the forward pass and then passing through decoder, you get this one. Also some sampling inside as well. Okay, this is the epoch. Okay, now we look at arithmetics of latent space. The arithmetic of latent space, we will select 3 men image, 3 women images. These are the original data, right? 25 images without glass and with glass, like without glass and with glasses. Some doesn't have that. With glasses, glasses. How come with glasses? This as well. All right. Okay. Then create a batch of image of men with glass. Average. Here is averaging. Right? Averaging after put it to encoder, then average them. So now you have representation of an average man with glasses, and then put it through decoder, and do the same thing for women. An average of multiple instances. So here, 3, right? Menji, and then put them through encoder. You have Menji encoding, then average encoding, just to get the averages encoding. Then put that into decoder, and then you get the reconstruction. Supposed to have women with glasses, and this is supposed to be women with glasses. And yeah. So we now have women with glass, men no glass, women no glass reconstruction as well. from the average of the 3 images. Okay, let's look at them here. These are the averages of men with glass, women with glass, men no glass, women no glass. I think the labels are wrong though. I think the label from the data set is wrong somehow. Yeah. I don't think so. Let's see. lt.im show. Oh no. I'm supposed to transform it back first. G shape. Oh, I see. Well, suppose that most of them are true. I mean, maybe we can just skip the averaging, but never mind. Supposed to be men no glass. Doesn't look men no glass. Women no glass. Okay. So here, yeah, let me do this instead. I think let's load the model. I think I test it out with the loaded one here. Yeah, they train a bit better than mine. Because like they train a bit more, a lot more actually, right? So when you look at this, it looks better in terms of contrast, in terms of color, right? Okay. Men glass, all right. Nah, wrong. Let's try. Okay. Here, men glass, women glass. Yeah, I think that they are the same. Maybe because of the randomization. Never mind. You can test it out then afterward. So here, men with glass, subtract women with glass, and then add women without glass. Then you have man without glass. Okay, you can do by not at the image, not at the image level, but at the latent vector level. Right? By doing adding and subtracting, averaging as well, you get the algebra of the latent space. And this is like one of the, I think it is one of the paper that, although it's quite underrated, is very revolutionized the field. And you can see that there are distinctions from just an autoencoder by adding in the distribution inside. You allow it to capture, by adding in distribution and a bunch of tricks inside, you allow it to capture distribution, capture variation that have consistent output. Okay. Okay, this is another example. Men with glass, not women with minus plus men without glass, men with glass. You can add women without glass and minus women without glass. Men plus with glass minus men without glass. So women with glass. But I think the encoding parts are wrong. I think the encoding part, because after you look at the sequence, they kind of not exactly lining up. Maybe because of the notation. Yeah, but you get the point, right? So you get the point here. Okay, lastly, let's compare them. GAN, you have adversarial networks. One compete with another, you have multiple agents try to compete with one another. These are trained through minimax and later trained to a more complicated manner of competing. You can think of it as a kind of reinforcement learning in a way that it learned from environment, multiple agents. Then the stability for this one is quite low, right? Not sensitive means not good, because it doesn't really, by competing with one another, it creates a situation that, well, one may use just shortcut to win, and then once it used the shortcut to win, is always just have that. It would be able to learn the distribution also, but the sharpness is high because everything's are encoded in the generators. It doesn't have latent structure. Everything's are implicit through, say, CGAN. Right? CGAN has the implicit conversion. The StyleGAN also encode everything into the network. But in VAE, while the quality is not that high, using elbow likelihood, it has single optimization, make it much more stable in terms of training. Just by train epoch, you already see the result. Actually, you can even see that it produced quite consistent in terms of adding, subtracting, although look not great. You train it a little bit more, then it would be better. The sharpness is lower. So that means, but you can combine it with stable diffusion. Right? Combine them together, now you have distribution representation, denoising, which is high quality. Right? Combine it together, you get quite good technique there. You look at diffusion first, then moving forward. Yeah. Yeah, like use it to generate things. It's quite great. But you kind of get it guided quite a lot. So VAE is still foundational component of today's generative AI. You see latent diffusion encoder decoder being used to generate high resolution image through diffusion model in the middle. Okay. That means when you use diffusion model, you also use it together with VAE to make it work in terms of representation. It has to be trained together. Has to be trained together a certain way. Then can be used together for that. It has efficient compression still, right, for the VAE. Compressed down, though quality is not that great, but still good in a way. You can then also structure the generative representation in a certain way to create, say, a certain different pose if you have a latent space demonstrating the pose itself. So usually now it would be VAE plus diffusion. Whatever diffusion that we are talking about, there are multiple names, but they are all diffusion model. Like in stable diffusion in 1.5, basic stable diffusion in the later Quen image in flux. Those are diffusion plus VAE here. And well, it make high resolution tractable in terms of learning by combining it together with the diffusion model. That leads to the next lecture. So this is all. You should try it out using Mark Liu notebook, and also PY will give you lab. What we have covered so far for generative AI. First, we cover GAN. GAN generate realism through competition. Unstable, work, nice. Then we look at VAE. Right? It now has structure. You can now do the latent manipulation with that. The next topic will be on the next topic that we will talk about VAE, not the next one, will be on diffusion model. Okay. The next one is on language model, if I remember correctly. Like we will just take a break from this because stable diffusion is too hard, but the math part is too hard. We will just take a break, pause a little bit, going back to the basic, looking at sequential generation. We look at RNN and sequence generation first, right? If I remember correctly. Or did I'm not sure now. Let me check. Okay. Right. Um, right. Right. The next one is on sequence models. Right. Combine RN without STM. But next week is exam one. Right. Next week is exam 1 week. And we won't have class on that week. Our class will resume again on the 23rd. Right? Am I right? I have to check my schedule. Okay, yeah, 23rd, which will be on the sequence-based model, sequence-based generation first. Then move through transformer-based generation. Then we look at the technique to do fine-tuning, and then concept of LoRa, PFT, prompt in the sequence engineering, in the sequence-based model. And afterward, we will then move through the diffusion with the basic first, the noise DDPM, DDM, DDPM, and then stable diffusion. Then we'll look at VOM as well afterward. Right. So yeah, that's all. And I will close like the first part of generative AI at this point. We now learn generative AI, right, the VAE. And then after the break, we will then look at sequence-based first and then jump back to a more complicated version of image generation, the diffusion model. I want you to see the sequence first. Maybe you will have some idea that you do diffusion other than image because there are quite a lot of combination that you can do there. Okay, now let's look at the lab. P Y, you can show the lab here on what have to be done.
Okay, so this is my be the one of the shortest lab introduction I have done. So the past lab involve a lot in coding, right? And I think I waste too much time of your in training. So this lab will be a write up one. So I have 7 questions for you. And what you have to do is try to discuss and answer those questions. That's it.
What questions are there?
It's a question about what we learned today. It's about autoencoder and variational autoencoder. So it ranges from the basics to the more advanced one. It's not ranked by the difficulty though, but yeah, you get the idea.
Okay.
Think of it as the change of like atmosphere. You have done a lot of code in the previous lab. This one, no code at all, but just answer this question.
Try to do it in your own words because it's very easy to just put this into AI and then get the output.
And I have to warn you, I know some of you using the generative AI to do the lab, and I caught that, okay, you, yes, and you get immediately 0 on that assignment.
If it's coding, you should do it yourself. But penalizable, than penalizable than writing.
Yeah, because coding you can get the idea of how to code from someone else, and but this is to test your ability to on this one.
So for this one, because the next week is also the exam week, it will be too much for you as well to have to code, to have to do the usual. So these are just some questions. You can just, based on the lecture that I have here, answer it in. You can answer it in just one sentence. Actually, a lot of these questions are like that. So yeah, homeworks more than lab. Um, yeah, submit it before the next week. And I would encourage you to set up the environment and try to replicate Mark Liu notebook. Okay, try to replicate that number 7, the link that I show you there, and then play with it a little bit in adding, subtracting of the latent space, and then you can see a lot of fun thing to do, right? And because it's just like when you have one image, one concept, you can add, subtract on others, right? And then generate something entirely new, yeah, out of those. Okay. All right. Yeah. So that's it. The work would be this, and then replicate the Mark Liu notebook. Don't have to submit that, right? But at least try to play with it to understand the concept of latent space. Latent representation will be important again. I think just in the next lecture, it's always very important in word to vect. But it will be important again when we talk about the fine tuning step. The fine tuning is the shift of the representation in a way. Okay.
Also, don't forget to follow this one on Mark Liu notebook. Yeah, they said that it's about the class data set has about 10% misclassification. So you have to like manually adjust the category of those images.
Which I didn't, obviously. Uh, that's the reason that they are quite strange and funny there. Okay. Right. Any question? Do you understand latent now? Latent means hidden. Right. Latent representation means that you have the hidden representative. Then with that, it can be combined. It can be you can do algebra with it, and then get the approximate output. So that means once combined, it produces the results like sampling X. So that's the main idea of VAE. It retain the sampling capability through the latent conversion. Okay, right. So yeah, anything you would like to ask? Online, on site? Let's look at online. Are there any questions? No. Okay. We don't have midterm exam. We have just the final exam at the end and the project, right? So for up to now, you would now have some idea in GAN, in VAE. You can actually you can see that the scope of the project doesn't limit you to anything. You can just play along with the VAE to do something, which is fine. Using different data set, playing with different things, doing tuning a little bit, doing a bit of modification to the training process from based on those are all fine. Put them into your project. Yeah, so I don't remember. Do we have the proposal? No?
No, I don't think so.
Okay.
No.
So we will have the presentation at the end on the 18th of May, the project presentation. Actually, I think some of the time here we will have to skip. And then that means some of the topic will need to be removed, yeah, or combined, because I will have to, I have like a duty to go as representative of the department to do some negotiation stuff. Won't be here on the 16th of March. So that means that there will be no class on the 16th of March. On the 9th should be fine, I think. Yeah, just 16th of March. Skip that, and then we will probably combine because LM engineering can be its own class. We probably don't have time to cover everything. We probably just look at the concept, combining it together with evaluation, ethics somehow in that. Or maybe just skip LM engineering because they are generative in a way. So maybe combine LM engineering with multimodal, because for multimodal we don't have resources. We only have time, not just resources, time as resources to train all the model. Think of them as grouping as advanced topic in generative AI in that, and then cover ethical aspects, and it should close in time there. Okay. If nothing else, then let's close the session. See you again next week. Oh no, the week after the next week, on the 23rd, we will resume the lecture on sequence models on RNN and LSTM used for synthesizing data. Okay, thank you everyone. Have a good night. Yeah, let's close the session.